Welcome to our last set of notes for the year on the standard model of particle physics. Okay, this is an interesting lesson because there is almost no math in this. This is simply a classification lesson. One of the goals of physics has always been to classify matter and to come up with what the building blocks of matter are. If we take all these things around us and divide them down to their smallest parts, what do we get? So we're looking at the building blocks of matter today. Our best picture of that today starts with what is known as the standard model. Okay, that's just the name for this particular theory. And it's not a theory as in we don't know if it's right or not. This is our best explanation of everything. The standard model attempts to describe the most basic of all particles that compose matter. We're going to learn a simplified version of the whole theory. Here are the charts in your reference tables. They're on the bottom of page 3, below the energy level diagrams. There are two sides to it. There's the classification of matter side, and then the particles of the standard model side. So, the way that this, let's look at the one on the left first. The way that this works is, at the top is matter, and then the arrows show how you can break down or classify that matter into smaller and smaller bits, or more precise and more precise things that we can then build off of. So you can see that matter can be broken down into, at its smallest level, so if you follow the arrows all the way down, matter is composed of things called leptons, if you follow that right arrow, and things called quarks. If you follow that left arrow all the way down, you get to quarks. Neither a lepton nor a quark can be broken down any farther than this. So the smallest bits are leptons and quarks. And if they can't be broken down, we say that they are fundamental. So you might hear us talking about fundamental particles. That means things like leptons and quarks that cannot be broken down any farther. Now, a lepton isn't a thing by itself. A lepton is just a name for a group of similar objects, similar particles. If we look at the particles of the standard model on this right-hand chart, they're on the bottom, leptons. Any lepton is found outside the nucleus. Okay? Leptons are affected by the weak, the electromagnetic, and the gravitational force, which makes sense because the other force of the four fundamental forces, the strong force, only acts within the nucleus. There are 6 types of leptons, as shown in the table above, which gives their name, their symbol, and their charge. And the one you're obviously most familiar with is the electron, right here. An electron is just a type of lepton. But in addition to electrons, we also have particles called muons, we have particles called taus, and then we have these other particles called electron neutrino, muon neutrino, and tau neutrino. So, some commonalities. So we have the name, the symbol, and the charge. If you look at electrons, muons, and taus, you'll notice they all have the same charge. They all have a charge of -1 elementary charges. And it's negative. That's the important part. The electrons, muons, and taus all have a negative charge. So, those 3 all have negative charges, and the reason that they're different is just their masses. I think muons and taus are much more massive than electrons, if I remember correctly. On the other hand, the other 3 types of leptons are called neutrinos, and I bet you can guess from their name and from the charge listing right there that they are all neutral. Each neutrino is neutral. And again, the reason that we have 3 types of neutrinos is because they all have 3 slightly different masses. By the way, the mass of a neutrino is really, 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 really small. Like, so small that we weren't really able to get a measurement of it for a very, very long period of time. Much smaller than that of the electron. So neutrinos are special because they are neutral, and they're very, very small. As a matter of fact, I think the word neutrino in Italian means like little neutral one. It's a diminutive. So those are the leptons. We have electrons, muons, and taus, all negatively charged. Muons and taus are a little bit bigger than electrons, I believe. And then the neutrinos, of which there are 3 types, electron neutrino, muon neutrino, tau neutrino, they are all neutral, and they're extremely small masses. The other type of fundamental particle, again, there's not just one quark, there are multiple types of quarks. Okay? Quarks are the building blocks that make up particles that are found in the nucleus. So you have leptons outside the nucleus, quarks inside the nucleus. And the weird thing about quarks, you can have electrons by themselves, but you will never ever see a quark by itself. They have to exist in a certain grouping. Okay? The table above lists the name, the symbol, and the charge for each quark. So the quarks all have, they have kind of funny names. So first thing you'll see up, down, charm, strange, top, bottom. And they're arranged like this because up and down quarks are kind of similar to each other. They were the first discovered. They're grouped together. Charm and strange have some similarities. Top and bottom have some similarities as well. They're kind of in different classes like that. So up, down, charm, strange, top, bottom. The names mean absolutely nothing. Those are just what people decided to call them once upon a time. The weird thing about quarks is if you look at the charges, you'll notice that all their charges seem to be fractions of an elementary charge. And this should set off warning bells in your head. Because I said a long time ago that it is impossible to have a fractional charge. It doesn't happen. You can't split an electron in half. And that's true. But when we look at quarks, for some reason, this is just how they're created. This is the one exception to the rule. Quarks are allowed to have fractional charges. An up quark has a charge of 2/3 of an elementary charge. A down quark has a charge of -1/3 of an elementary charge. Charm and top have the same charge as an up. Strange and bottom have the same charge as a down. And so this is the only exception to the rule that there can never be a charge less than the charge of the electron. I don't make the rules. That's just how it works. Okay? So therefore, any combination of quarks whose charges do not add up to a whole number. Remember I said quarks come in certain groupings. If you have a grouping of quarks and that grouping still has a fractional charge after you add all those charges up, it is impossible. That grouping of quarks does not exist. You will never see that in reality. Impossible. Not a real particle that can be observed. Okay? Any combination of quarks whose charges do not add up to a whole number is impossible to have. It is not a real particle that can be observed. So let me show you an example. Say that you were proposing that maybe there's a particle that is made up of an up and a charm quark. Up and charm both have charges of 2/3 of an elementary charge. Adding those together, you get 4/3. That's still a fraction. Therefore, it's impossible, and an up and a charm quark would never come together to make a real particle. On the other hand, what if you had an up, a charm, and a top quark? 2/3 plus 2/3 plus 2/3 is 6/3. And that's not a fraction anymore. That's just plus 2 elementary charges. That is a particle that can exist. That particle does exist. I don't know what it's called, but that particle can exist. That is within the limits. Okay, that is within the rules. So the rules seem very arbitrary to you, and to be honest, yes, they are. That's just how these things seem to work. Okay, there's never been a particle observed that has a fractional charge outside of the individual quarks we know about. And again, those individual quarks, they don't exist by themselves. They always exist in groups. Okay, so one of your questions might be, well, if they always exist in groups, how do we know that there are quarks all by themselves? And that's a good question. There have been many other experiments that I've done that have reasoned that these particles are actually made up of smaller particles within them. That's going a little too deep for what we need, though. Okay, so particles that are made up of quarks, groups of quarks, have to have whole number charges. The quarks themselves have fractional charges. The particles that they compose must have whole number charges. Let's first talk about baryons. We see that quarks can make up a baryon if it's a grouping of 3 quarks together. So if 3 quarks are arranged together, they create what is known as a baryon. These types of particles are fairly heavy. You have 3 different quarks. It's kind of a lot of quarks. The most common baryon, or one of the most common baryons, is created by combining 2 up quarks with a down quark. Now, real quick, let's keep going. The particles are created by combining quarks, are symbolized by combining the letters representing each quark. So this one would be called, we have 2 up quarks and 1 down quark, up, up, down, U, U, D. Now, what would the charge on that be? An up quark has a charge of positive 2/3 of an elementary charge. Down is negative 1/3 of an elementary charge. So if you take positive 2/3 E plus 2/3 E minus 1/3 E, 2/3 plus 2/3 is 4/3, minus 1/3 is 3/3. Well, 3/3 is just 1. Plus 1E. So the particle that is made up of 2 up quarks and 1 down quark would have a charge of positive 1 elementary charges. Interesting. Do you know of any particle that we've studied this year that has a charge of plus 1 elementary charges? You're right. It's a proton. A proton is not actually fundamental. A proton is made up of 3 quarks coming together, 2 up quarks and 1 down quark. So you would say a proton's quark composition is up, up, down. And if you look at those charges, they add up to give us the charge of a proton, okay, plus 1e. So a proton is very, very small by itself, but it can be, we know that a proton is actually a combination of 3 quarks coming together. There's one other baryon that you actually know of and have studied so far this year. It's created by combining 1 up quark and 2 down quarks. So the quark composition, or the label for this, would be UDD. U has a charge of positive 2/3 E minus D, 1/3 E, minus another 1/3 E. 2/3 minus 1/3 is 1/3, minus another 1/3, well, that's 0, which means a charge of neutral. You know of any particle that has a neutral charge? Kind of obviously, it's the neutron. Remember, leptons are completely separate from this. Leptons are not made up of quarks. Leptons are their own group. So you can't take quarks and have them make up an electron. It doesn't work like that. Quarks compose the particles in the nucleus, like protons and neutrons, and many other things as well. I just wrote neutrinos. Better known as the neutron. That is a good lesson for me to just stick to what I need to say. All right. So there are many other weird particles that get created by combining different types of quarks, but for the most part, they are extremely unstable. One of the weird things about quarks is they don't really last that long. If you have, or in certain combinations, if you have, let's say, like an up, a charm, and a top quark all together, they won't last very long that way. They will decay or change into other things very, very quickly. Kind of like radioactive decay a little bit. They will change very, very quickly into other things. And usually they all break down into protons and neutrons, which don't tend to decay. Okay? All right, I'm actually going to pause there, and we'll set up for the last 3 topics, and then, well, you'll be done.